Hi, Assalamualaikum. My name is AL-AMIN and welcome back to my video. Today I will present about the basic of industrial programming. My presentation basic from the two questions I get from my lecturer, question 1 and question 2, and I will explain about how programmable logic control PLC works on industry right now. So without wasting our time, let's go to the question 1. So let's begin with question A, 1A. The difference between a general purpose computer and a programmable logic controller or PLC. As you can see in this table, a general purpose computer like your laptops or desktop at home runs operating systems such as Windows, Mac OS or Linux. It is designed for clean environments like an office or a home. You use it for browsing the internet, writing documents and programming or data entry. Its strength is flexibility. You can do almost anything with it, but its limitation is reliability. It can crash, freeze or overheat, especially in dusty or hot conditions. A PLC, on the other hand, is built for the factory floor. It doesn't run Windows or any regular operation system. Instead, it uses real-time firmware that never crash the way a PC does. It can handle dust, heat, vibration and electrical noise. PLCs are used to control motor, conveyor, valve and sensor. Real-world machine, they are stretched in extreme reliability during 24 hours a day, 7 days a week. Their main limitation is cost. They are expensive and they are not good for complex computing tasks like heavy maths or graphics. So now let's go to the question 1B. Why the big company or factory spend 5,000 ringgit on a PLC instead of just 50 ringgit on a microcontroller? So I have 3 main reasons for this question. The first, the factory environment. A microcontroller is delicate and can fail in heat, dust or electrical noise. A PLC is built out of this condition. Second, reliability. A PLC runs for a year without crashing, but a microcontroller can freeze or reset. In a factory, even 1 minute of downtime can cost thousands of ringgit. The third is safety and maintenance. PLCs meet international safety standards. They are modular and can be reprogrammed online. Microcontroller needs full redesign and offline change. So while a microcontroller seems cheaper, the true cost after adding protection, testing and downtime risk is often higher than the PLC. Factories pay for reliability because stopping production costs far more than 5,000 ringgit. For the next, we go to the question 1C, digital I/O versus analog I/O. Digital I/O is simple, on or off. A push button gives either 0 volts or 24 volts, nothing in between. Analog I/O is continuous range. A temperature sensor gives varying signals, 4 mA for cool, 12 mA for warm, and 20 mA for hot. Why can we plug an analog sensor into a digital port? Because a digital port only understands on or off. It cannot read in between value. You will get random or unreliable result. Why does analog starts at 4 mA instead of 0 mA? It's called a live zero. 4 mA means minimum reading and 0 mA means a broken wire. If it starts with a 0 mA, you could tell me the difference between the zero reading and a broken sensor. Starting at 4 mA makes troubleshooting safe and more easy. So that's all for the question 1. So let's go to the question 2. Question 2. Imagine you are an automation engineer explaining a new bottling line to a client. In your presentation, you must define the I/O list and explain the logic flow. Now let me explain the I/O list for this bottling line. First, the input. The sensor, we have 3. The bottle percent sensor is digital. It tells the PLC when a bottle arrives at the filling station. Next, the fill level sensor. This one is analog. It continuously measures how full the bottle is using 4 to the 20 milliamp signal. Third is the index sensor, analog digital sensor. It counts bottle as they move along the conveyor. So now let's talk about the output, the actuator. First, the conveyor motor. This is a digital output that moves bottle forward. Second, the fill valve solenoid, also digital. The PLC open it to pour liquid and close it when the bottle is full. Third, the stop gate, a digital output that holds the bottle in place during filling. during filling. In short, sensor are the eyes, actuators are the hands, and the PLC are the brains for this system. So now let me walk you through the step-by-step logic flow of the bottling line. The sequence has 4 steps: detect, stop, fill, and move. Step 1, detect. The PLC continuously reads the bottle percent sensor when a bottle arrives at the filling station. The sensor sends a digital to the PLC, a signal to the PLC, and now the system knows the bottle is ready. Step 2, stop. The PLC immediately turn off the conveyor motor. At the same time, it engaged the stop gate, which extend out of physically hold the bottle in place. This prevent the bottle from moving during filling. Step 3, fill. The PLC opens the fill valve solenoid. Liquid start pouring into the bottle while filling. The PLC constantly monitor the analog fill level sensor. The signal rises from 4 milliamp to empty to for from milliamp for empty to 20 milliamp for full. Once the PLC detects 20 milliamp, it knows the bottle is full and immediately close the valve. Step 4, move. The PLC reacts the stop gate to release the bottle, then it starts the conveyor motor. The fill bottle move down the line and the next empty bottle arrive at the station. The recycle then repeat automatically from the step 1. This detect stop fill move sequence runs continuously 24 hours, 24 hours a day, 7 days a week, with no human intervention. That is how PLC automation powered the modern bottle line. So, for the conclusion, we have learned that PLC are rugged, reliable, and built for harsh factory environment, while general purpose computers are flexible but fragile. Factories spend more on PLCs because even 1 minute of downtime can cost thousands of ringgit. We also saw the difference between digital I/O, which is simple or on or off, and analog I/O, which is used a continuous 4 milliampere signal to 20 milliampere signal, starting at 4 milliampere to detect broken wires. Finally, we walk to a bottle line where sensor act as the eyes, actuator as the hands, and PLC follow a simple but powerful logic flow: detect, stop, fill, and move. That is the basic of the industrial programming. Thank you for watching, and that's all from me. Thank you very much.